Hi, my name is Roberto Martinez. Enrique and I will be going over our CFD project. But first, I will talk about what CFD means, which is computational fluid dynamics, as well as its components. It is a use of computer-based simulation to analyze fluid flow, heat transfer, and other related phenomena to help us solve for velocity and pressure fields. And it uses Navier-Stokes equations, as well as it uses four Navier-Stokes equations, conservation of mass and momentum, average and Rand's equations, solved numerically using CFD, several Rand's-based models offered in ANSYS. CFD is important because it helps us budget the design making it cheaper than experiments, more flexibility, more in-depth analysis, as well as to visually see heat, momentum, and mass transfer, and understand the verifying existing system and identifying the problems. One application used for CFD is aerodynamics, such as aircraft and vehicles, to find the lift and drag forces and to visually see airflow through and around objects. You can also use CFD for turbo machines to see the flow inside rotating machinery, such as turbines, jet engines, diffuser, fans, so on and so forth, as well as for electronics, for their circuit boards, to see airflow, heat management, pinpoint hotspots, and to predict the temperatures. The fourth application is sports. In golf, soccer, football, etc., to analyze its aerodynamics. Like for the golf ball, you can see the pressure and how the air circulates around the golf ball. The fifth application is biomedical engineering to help us understand the blood flow and heart pumping, respiratory system, spinal fluid flow, designing artificial organs. The sixth application is in meteorology to predict weather and to track storms. The last application is in hydrodynamics to design ships, to predict flow patterns, as well as to simulate physical effects. Our CFD problem consists of a 3D laminar flow through a pipe with 5 inlets and 1 outlet. All inlets have different temperatures, and we'll be finding the velocity and temperature at the outlet.
In order to solve this problem, we're going to be using the fluent flow analysis system in ANSYS Workbench. So to start, we want to make sure that our problem is in 3D, so we want to make sure that the system is set to 3D, the analysis type. And we open a new designer geometry. Once the design modeler opens, the first thing we want to do is change our units to millimeters. So we do that by going up here and changing the units to millimeters. And also, if you want this grid, you can go to the sketching settings and turn on the grid and snap. So we're going to start off making our geometry by just making it out of simple lines. Like so. We're going to start off by making a 2D sketch, and we'll be making it into 3D after. And once you're done making your 2D sketch, you're going to want to use the dimensions tool to dimension it. So here we have our finished 2D sketch with the dimensions put on it, but we haven't set the dimensions yet. So first off, for our angle here, we're gonna want to set that to 150 degrees. And then for this length right here, we're gonna want to put that to 400 millimeters. For this dimension right here, we want to set that to 10 millimeters. For this dimension right here, this one right here, we set that to 150 millimeters. And finally, for our last one, we will set that to 30 millimeters. So now that we have our 2D sketch set and dimensioned, we want to make it into 3D, and we're going to be using the revolve tool right here to do that. So select it, select the sketch as the press apply, and the revolve axis, we're going to be using this line right here. And it should revolve 360 degrees. So now we just press generate and we should get our 3D geometry. There we go. As you can see, we now have the start of our pipe. We still need to add our 5 inlets, but here we have our pipe. So now what we're going to want to do is we're going to want to get rid of these sharp edges right here on the pipe wall. These right here. And to do that, we're going to be using the blend tool. So the blend tool is right here. And we are going to select both our edges. Oh, make sure to hold control to select both edges. And we're going to want to set this to 20 millimeters. And then we press generate, and it smoothens those edges out. Next, we're going to want to create a new plane on one of the faces of the pipe so that we can draw our inlets. So we're going to use the face select tool and then the new plane tool to create a new plane on this face. And from this plane, we can sketch our inlets. We press generate, and you can see we have a new plane right here. So to create our inlets, we're gonna start here. We're gonna sketch a circle using the circle right here on this axis, and that will be one of our inlets. After, we're gonna want to dimension it. I want the height and the diameter. And the diameter should be 10 and our height should be 20 millimeters. To create our pipe inlet, we're going to want to extrude the circle using the extrude right here. So for our geometry, we use the circle, which should be sketch 2 right there. We want to make sure the operation is add frozen because we want this to be a separate component, separate part, and we want to extrude it 50 millimeters. So we press generate, and there we have our extruded inlet. This is just one of them, we do need 5, but here you can see that we have 2 separate parts, 2 separate bodies. So as I said before, we want 5 inlets. So in order to create more inlets, we can use the create and pattern right here. And for our geometry, we use the inlet we already have. And for direction, we want to use the YZ direction. So we go up here. Go right here and select the direction we need, which will be the YZ direction. And we click apply. For our pattern type, we want a circular pattern. And we apply our axis of rotation for our circular pattern. This is to create our 4 other pipe inlets by making a pattern, circular pattern, copying the inlet we already have. We want them to be evenly spaced, and we need 4 copies because we need 5 inlets in all. So we click generate, and here we have our 5 inlets. As you can see over on the left, we now have 6 bodies, 5 inlets, and then the pipe itself, which includes the outlet. So now we're done with the geometry. We can close that out and we can open our meshing by just double clicking on our meshing here. So now that the meshing window has opened, we can create our meshing for our pipe. And we go to mesh control, and we pick the sizing option here. And we're gonna use body sizing to create our mesh for this. And we want to select all 6 bodies, so we hold control down to select all 6 parts. Press apply. Now for our mesh element size, we decided to go with 6 times 10 to the negative 4. So we go. We want the behavior to be hard for our meshing. There we go. And now we just press up. And here we have our mesh has updated, so now we can see what it looks like. And as you can see, it looks pretty good. And if you want a finer meshing, you can make the element size smaller. However, ANSYS might not run well enough to make it smaller. So, and conversely, you can choose to make it a larger element size, which will give you a less fine meshing, but it should still work the same. So now what we want to do is we want to use the face select tool to press on the faces, the inlets, and right click on them. And at the bottom you should see a option that is called create named selection, and we want to name our inlets inlet 1, inlet 2, inlet 3, inlet 4, and inlet 5. So let's go through that. You can also press N after right clicking to open the named selection option. Now we also want to name our outlet here, so we press on that, right click, and we name it outlet. And then we also have to do our pipe wall, so we have to select the entire pipe wall. Select these as well, and we name it our pipe wall. So there we have our named and the mesh. We also want to select the entire pipe, all the parts, and we will name it the fluid domain. So now we're done with the meshing. We can go ahead and open our setup, and it got cut off from the recording, but we used double precision and 4 parallel processes. And then the next thing we want to do is we want to check our meshing, make sure that everything is good. And once it is, confirm that it's good. Next thing we want to do is go here and turn on the energy equation because we are looking for the heat transfer. So we want to make sure the energy equation on, and we leave the flow as laminar. So now we want to go to our materials and change it to water. And at this point I realized that the recording I was using wasn't recording pop-ups, so I put this here to show what it looks like. Once you press on the materials, you should get a screen that looks like this, and you should change air to water by going to the Fluent database, which is right here. If you scroll down, you'll find water liquid H2O L for liquid, and you want to copy paste that and then change / create, and then you can close that to change our materials. Next, we want to set our boundary conditions. Before boundary conditions, we need to set a cell zone condition. We want the fluid domain to be water liquid, just right here, drop down menu. And then for our boundary conditions, we want to set our inlet conditions for all 5 of our inlets. So all 5 inlets should have velocity 0.01 meters per second. And then from there, we want to change the temperature for all of them. We want them all to have different temperatures, so we set them to 290, 300, 310, 320, and 330 Kelvin. And then we want to change our outlet type to outflow. And then we also want to make sure our pipe wall has a heat flux of 0 so that it is adiabatic. Now for our solution method, we went with simple C, and we made sure that everything here was least squared, cell base, second order, and second order upwind. Next up, we have our residuals. So for our residuals, in order to get a more accurate solution, we set our residuals to 1 times 10 to the negative 6 for more accurate results. So we set them all to that. And then for our initialization, we set standard initialization, and we set it to compute from all zones. And when you set it to compute from all zones, you should notice that this temperature down here changes from 300 to 310 Kelvin. Then we run our calculation. For our calculation, we ran it at 1000 iterations, and our residuals look like this. And then to get our results, under the reports section, which is right under the calculation, we use the surface integral reports under the calculations, and under reports you will see surface integrals. And then for the report type, we set it to the facet average, and then for the field variable, we set it to velocity. So we found velocity at the output, and we selected all the inputs and the output, and here you can see our results. And we repeated the same steps to get the temperature at the output. Here you can see it a little bit better. The under results, we go down under reports and we press surface integrals, report type, facet average, field variable, velocity to get velocity, and then temperature to get temperature. Select all our inlets and our outlet, and then we press compute in order to get our average velocities at our outlet and our temperature at our outlet, which is what we were looking for. And that's it. So we completed our problem. So we successfully used ANSYS Fluent to solve the problem. Thank you very much.